Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends. As a continuation of the previous lecture on environmental loads, this is lecture number 26, which is continued with wave loads of the SwayamPrabha course titled Maritime Structures, Types, Construction, Pre-Service Analysis and Design, which is offered by the Department of Maritime Engineering at IIT Gandhinagar. We already know that environmental loads form a very major part of external exciting force on any maritime structure, and they have dynamic effects because they vary with space, time and depth of water. So we learned in the last lecture that how the water particle kinematics or the sea surface elevation governs to obtain the water particle kinematics. To be very in a simple form, Airy idealized this as a linear wave theory and help us by giving the water particle kinematics equations from which we should be able to derive the forces which are called otherwise hydrodynamic forces. Hydro because from water, dynamic because they vary with space, time and water depth. It also helped us to now classify the water depth as shallow, intermediate and deep waters based on the wavelength and the phase speed. We already defined this in the last lecture. I believe that you have gone through the last lecture before we attend this lecture. This is a sequence lecture, environmental loads 2, where wave loads is continued to be discussed in this lecture 26. So, friends, welcome to lecture 26 on wave loads on maritime structures. So, in the last lecture we said that water particle kinematics which will give me the horizontal water particle velocity as a function of space and time, and of course, the water depth as well, and the vertical water particle velocity as a function of phase and time, and horizontal water particle acceleration and vertical water particle acceleration, which we gave the equations, should help me to find out the hydrodynamic forces. Okay. Now, the major question comes, how to get these forces, because we know by idealizing it as a simple sinusoidal single wave, what Airy called as a regular wave, in reality let us reiterate that sea surface elevation is random, which is a series of sum of many regular waves, okay, of different amplitudes, different phase angle, etc. We picked up any one such wave and showed here. So, for one such wave I can compute the water particle kinematics, I can find the force. If I want series of waves, then I should go for a spectrum, which I will discuss this in this lecture. Okay. So, having said that we know how to compute these, let us see how do they vary. So, if I draw a simple regular wave and if I mark the sea bed and also note the water depth in meters, we know this point is referred as crest and this point is referred as trough, and we know that the length of the wave is dependent lambda, which is also known as a function of the wave period. Therefore, at any point along the depth, for example, I have a member, an offshore member, a cylindrical member, which is, let us say, fixed at the seabed. The cylindrical member has got an axis somewhere here. The cylindrical member also has a dimension of diameter d. Now, on this member I want to find the force acting on this member at any depth measured from the mean sea level. So, y is measured from the mean sea level. For example, y is 0 at MSL and y is d at the seabed. Okay. So, I pick up any point, let us say I want to find the force at this point, and I say it is going to be a force at the depth y at the point A. Let us say this is the point A. So, A has got the x coordinate from the origin, it has got the spatial coordinate in terms of time, and now it also has a depth coordinate in terms of y. So, if I know this value fed in the system, I will be able to get u dot as x of t, which was just given as omega h by 2 cos hyperbolic ky by sin hyperbolic kd times of cos kx minus omega t, where omega is the frequency of the wave and t is the time at which I want to compute. So, it is a function of time, and x is the point where you want to compute in spatial distance. If you take this as origin 0, 0, there is going to be, then x in our case going to be minus d by 2. Okay. Y is known to me, t I can compute. So, t is going to be the variation, that is why it is called hydrodynamic, right. So, I can find the water particle velocity in terms of time from this equation, for example. Okay. Now, I want to know how to compute the force. I am interested not in the velocity. how this compute the force. Let us see that. So, what are the different forces that act on maritime structures? So, there are 4 kinds of forces which act on maritime structures. One, what we call as Frau-Krailau force, which essentially caused by the pressure effects due to the undisturbed waves. Okay? That is very important. Undisturbed incident waves. Let me underline the term undisturbed. Okay? That is a static, more or less a very less variation in terms of time and dynamic effects. So, the pressure effects caused by such waves will induce what is called FK force on any structure. The second could be the diffraction force, which is again caused by the pressure effects in the presence of the structure. For example, if you have a wave field, the wave field will cause pressure effects which will induce FK force. If I have a cylinder placed in the wave field, then this is going to cause a disturbance, right? And this disturbance will induce something called diffraction force. So, I would say this is caused because of disturbance present in the wave field. Okay? The third one is the hydrodynamic added mass. And potential damping force. This is again caused by the pressure effects which arise when the structure is in motion. Let me underline the word. So, this is more applicable to floating structures, ships and compliant offshore structures. Let us go back. This is more applicable to fixed offshore structures. This is more applicable to undisturbed surfaces or incident waves. Okay? So, we will talk about diffraction and hydrodynamic added mass and potential damping, which is a very important force vectors acting on maritime structures. The last one is the viscous drag force, which actually drags the structure because of viscous effects. This is also caused by the pressure effects. So, this is essentially caused by the relative velocity between the fluid and the structure. So, I can now say viscous drag effects are more important in floating structures, ships and compliant offshore structures. Okay. So, now we got 4 sets of forces, right. Let us see what are the approximations we have in this. What are the approximations? The Freud-Krylov force and the diffraction force are idealized as single inertia term. Okay. Now, it is true when it encounters a slender structure. Now, what is a slender structure? Slender structures are those structures whose d by L is less than 0.2. This slenderness is not because of structure, it is not a structural property, it is a hydrodynamic characteristic of a structure. Now, d is the diameter of the structure, to be very specific, outer diameter of the structure, and L of course the wavelength. So, depending upon the ratio between the diameter and the wavelength, we find out something called the characteristic dimension of the structure, and if that value is less than 0.2, we call that member as a slender member. The slenderness is not related to the structural property which is causing buckling, where we learnt in the previous lectures. Okay? This is hydrodynamic characterization of a member in maritime structures. Okay? So, now the slender structures are true to find out this. Now, when the force encounters the structure, structure reacts. So, therefore, the reaction forces produced or offered by the structure are proportional to the acceleration of the structure and this results in added mass, which is an inertia force. Okay. Further, the reaction forces proportional to the velocity of the structure results in damping force. So, friends, in simple terms, acceleration of the structure causes added mass effect, which causes inertia force. Velocity of the structure results in damping force, which is Fd. So, these are the forces which are generated as a reaction force from the structure if the structure is in motion. Okay? This is true for compliant structures, ships, floating structures, because they all will be in motion. Now, let us come to an argument. After knowing the horizontal water particle velocity, horizontal water particle velocity, horizontal water particle acceleration, vertical water particle velocity, horizontal water particle acceleration, vertical water particle acceleration, I can now should be able to find out the force. Okay? Morrison helped us to find out this force for elemental length of the member. So, Qn, the force per unit length of the member, is given as rho dV An plus Cm minus 1 rho dV An minus x double dot n plus half rho Cd dA Vn minus x dot n of Vn minus x dot n, absolute. Okay, let us look at this equation carefully. Rho is a specific density of seawater. Okay, so the rho value I will write down here for our understanding. The rho value for seawater is 1025 kg per cubic meter. You may ask me a question, seawater density is only 1000, water density is 1000 kg per cubic meter, why seawater is 1025? Because seawater contains lot of minerals, salts, etc., the density is higher. Okay? So, 1025 kg per cubic meter. N and Vn are acceleration and velocity of the structure. Sorry, An and Vn are acceleration and velocity of the water particle. X dot n, x double dot n are velocity and acceleration of the structure. So, let me mark n and Vn or acceleration and velocity of the water particle. Okay, let me write down that here. An Vn or acceleration and velocity of water particle. We already know that, is it not? We have used for acceleration, we have used u double dot and v double dot. This is horizontal, this is vertical. Okay. Now, I am saying in general An. For velocity, we have used u dot and v dot, which is horizontal and vertical. I am saying generally Vn. Okay. N stands for the subscript of these acting normal to the member. Normal to the member. Okay. If I have member, these are acting normal to the member, perpendicular. Okay. That is why it is N. Cm in this equation and Cd are called hydrodynamic coefficients. Cm is called inertia and Cd is called drag coefficient. I can write it here. Cm is called inertia coefficient and Cd is called drag coefficient. Both are hydrodynamic coefficients which are given in international codes of practice. Okay, they are given. For example, Cm is approximately 1.2 to 2.0, Cd is approximately from 0.6 to 1.0. These are given in international codes. Of course, the CDCM depends on Killigan-Carpenter number, Reynolds number and surface roughness. So, one can experimentally estimate them and literature has a lot of support on estimating CD and CM, but as a designer of marine structures, I want to know a definite number. So, now I say these values are in this range. Okay. The drag coefficient varies from 0.6 to 1.0, the inertia coefficient varies from, drag coefficient varies from 0.6, sometimes literature says 1.2, okay, and inertia coefficient varies from 1.2 to to 2.0. I can pick up a number relevant to that particular type of structure, depends on the Reynolds number, the Killigan-Carpenter number and the surface roughness. Okay. These details more can be seen in other parallel course on wave hydrodynamics, which I am not covering it here, but for information sake we are giving this information to all of us. Okay. Let us go back to this equation again and try to learn what other parameters we do not know. Okay. Let us mark what all we know. We know rho, so we will mark rho. Okay. We know xn and x double dot n. We know Vn and V double dot n. So, what we do not know is dV and dA. Let us explain that. dV and dA are essentially the volume and area of displaced water, okay, per unit length of the member, per unit length of the member. Okay. Now, I can look in this equation, rewrite this equation. Q1 can be rewritten as, just combining the terms, I can say Cm rho dV an minus Cm minus 1 rho dV x double dot n plus half rho Cd dA Vn minus xn dot Vn minus xn dot. Friends, please note there are two terms here. One is an absolute term which does not release the signal or the sign between. For example, if the velocity of the water particle is larger than the velocity of the structure, then this term will become positive. Vice versa becomes negative. So, if I have this absolute removed, okay, so minus and minus will become plus. It means this component will be always an addition, right. To avoid that, to prevent this and to protect the directionality of the force, we use this mod function, so that the sign convention is protected. For example, if Vn is greater than Xn, then this becomes positive. If Vn is lesser than Xn, then this becomes negative. So, therefore, this term is deducted. So, that protection is done by putting a mod sign here. Okay? And this also makes the drag term nonlinear. Is it not? Because there are two terms here. There are two terms here, it also makes it nonlinear. Okay. So, nonlinear drag, okay, and inertia. Okay. So, that is what the equation is all about. Now, there are two main issues with this equation. What are those two main issues? This equation is in the relative motion formation, is it not? Because it has got a relative term. See here, relative term. This is valid only if the structural motion is large. That is, it is true and good applicable for floating and compliant structures, not for fixed structures. Okay? For fixed structures, you cannot use this. Secondly, the second issue is the relative velocity term which produces drag. It also produces the damping force. Okay. There are two issues which are focused on this specific equation. Now friends, if I have got a member whose diameter is very large, let us say I have a member whose diameter is very large compared to the wavelength, we know if d by L is less than 0.2 or d by lambda, let us say d by lambda is less than 0.2, for a diameter being very large compared to this, we know this is slender member. Okay. So, if h by d is very small, then viscous force becomes less significant. So, we call this as drag dominant structures. Okay. In such cases, detailed numerical methods are used to compute the forces. Now, the question comes, we have been doing this analysis for a single wave. If we have series of waves and make them as irregular, how to get the forces? Okay. In that situation, we will go for a spectrum. Spectra represents the irregular or the random phenomena of sea waves. There are many spectra available in the literature. Okay. Before looking at the spectra, let us look at some terminology. For regular waves, an extreme wave is represented by h and t, that is period and wave amplitude. For random waves, the energy density spectrum is used. The variables of energy density spectrum are as follows. Variables are as follows. Let us see what are they. One, we call short term record length, which is Ts. It indicates duration of the storm. 2, significant wave height, which is indicated as Hs. It is actually the average height of the wave amplitudes of the highest 1/3 wave heights. Okay. For example, if I have a table, number and the wave height, so 1, 2, 3 and 10 or 100, wave height 1.5 meter, 1.6 meter, 2.1 meter, 1.4 meter and so on. What I will do, I will first arrange them in descending order. Okay, keeping the maximum wave height at the top. Then I take an average. I take 1/3 of this. I take 1/3 of the record and find the average of that. That is what we say as Hs. So, average height of wave amplitude of top 1/3 record, right? That's Hs. Then we find RMS, root mean square of the wave height, which is H RMS. This is the root mean square of individual wave heights in a short record. Peak frequency, which we call as omega naught. This is the peak frequency of the spectrum. 5. Significant wave frequency, which is omega s. This is the average frequency corresponding to the significant wave height in a short term record. Let us say what is mean frequency, which is omega bar. This is the mean frequency of individual wave in a short term record. Based on this, there are many spectrum available in the literature. Okay. The commonly used spectrum wave spectrum is Pearson Moskowitz spectrum, called as PM spectrum. So, this is given by an equation. The spectral ordinate S omega is given as alpha g square by omega to the power 5. Omega is a variable, okay? Exponential, that is e power minus 1.25 omega by omega naught raised to the power minus 4. Okay? Alpha is called Phillips constant, usually taken as 0.0081. Omega is a variable in this equation. Okay? We are plotting this against omega. For example, this will be omega, this is S omega. I am going to plot this way. Okay? G, of course, we know, accelerating due to gravity, and omega naught we already know, peak frequency. Okay? I can plot the spectrum for different values of omega, and typical spectrum looks like this. Omega, yes, omega looks like this. So, this is omega naught. Okay. So, if we have the spectrum, I can then find the relation between omega 0 and Hs. So, 0.161 G by Hs. So, if I know the significant wave height, I can find omega naught. Further, I can also find the energy of the power spectral density function of the wave spectrum, which is given as 1 by 8 rho g h square. So, there are furthermore spectrums in the literature, which is modified PM spectrum, John Swap spectrum, Brescinger spectrum, ISSC, International Ship Structural Congress spectrum, and so on. So, I would request the viewers to look at the reference literature of my book cited in this particular course for learning more about the spectrum, the MATLAB programs and the plots. Typically, the spectrum looks like this. If I want to plot omega versus omega 0 and I want to plot S omega, and I would say the spectrum looks like this. Okay. So, this is John Swab. And this is PM. So, the peak is slightly shifted between these two at 1.0. Okay, there is a small shift between this, and the unit for S eta omega is meter square per second, and so on. Okay. So, I would request the viewers to look into this, and therefore, the spectrum will now give me the energy which is exerted by these waves on the structure. So, I can also find the force based on this way for irregular waves. So, friends, let us look at the summary. In this sequel lecture, we discussed about the random waves. We looked at some terminology. We also learnt about the equation for power spectral density function of the PM spectrum. We know how to compute the energy imposed by a random wave on a structure. We also learnt about more spectra, which you will also further learn from the additional references. Friends, so now we understood how to compute the wave force on any member at any distance x, any depth y at any time t, if I know the water particle kinematics based on Airy's theory. Okay. So, based on Airy's theory, we know the water particle kinematics. Derived from that, I use Morrison equation and I try to find out the force per unit length of the member at any depth, any point, any time I want. So, this is what we call as hydrodynamic force exerted on members of maritime structures. Should you have any doubt, please post the questions and observations in the website in the discussion forum of this course. Instructors will get back to you with the doubts cleared on that as soon as possible. Thank you very much. Happy learning.